Hi everybody. Today's video is going to be on section 8.2, area of a surface of revolution. So recall in chapter 6, we learned how to use integrals to find the volume of a surface of revolution. And remember, you learned something called the disk method. You learned something called the shell method. In this section, we talk about surface area. Okay? So what is surface area? Surface area is simply taking a three-dimensional figure and figuring out the area of the surface of it, right? So the area of a surface of revolution is the area of the surface if it were flat. In other words, what you do is you take the surface and you, kind of like pretend you were wrapping it with wrapping paper or painting it or something like that. And that would give you the area of the surface. Okay, so as an example, let's look at a cylinder. So a cylinder looks something like this. It's got a radius, and it's also got a height. And suppose we wanted to know what the surface area was of this. And for now, what we're going to assume is that it's hollow. In other words, we're going to assume that there's no top or bottom here. So assume there's no top or bottom. So what would the area be? What you could do is you could think of the way that a soup can is wrapped with paper, right? So what you could do is you could take this thing and unroll it. So it's going to look something like this, right? It's going to look something like this when you unroll it. And so it's really just a rectangle, isn't it? So this becomes this rectangle, and this height stays the same. However, we need to figure out what the top dimension is. So let me actually use a different color for this. Let me use green here. If we were to color this in green up here, that green actually ends up being this entire thing. And so if we want to know what that length is, we just need to figure out how far it is around the circle. And we know what the circumference of a circle is, right? It's 2 pi r. And so the area is equal to 2 pi r h. 2 pi r h. Okay, so now what we're going to do is we're going to move on to some more complicated shapes, okay? And the one that we're going to look at is something called a frustum. So what is a frustum? A frustum is a shape that looks like this. I want you to picture like a big cone. So you could imagine a imagine a big cone, and then you take away the small cone on top, and you're left with what's called a frustum. Okay, so this is our frustum. So what we would like to do is we would like to figure out what the surface area of this shape is. Again, assuming that the top and bottom are open, right? There's no top or bottom. So let me just write that down. There's no top or bottom here. So how would we find the surface area of a shape like this? Well, let me actually make this look slightly nicer. So what I'll do is I'll use a straight line here. Something like that. So we're going to assume that the top guy has radius R1 and the bottom guy has radius R2. And then we're also going to assume that this length, that the side length is just L. Okay? So if you were to look at the area of such a thing, you would actually write down that this is the area of the big cone minus the area of the small cone on top, right? And if you actually go through the derivation, what you end up getting is the following. You end up getting that this is pi times L times the sum of the two radii. Okay? But what you can do to make this look a little nicer is you can multiply by 2 and then divide by 2. And the reason we're doing that is because R1 plus R2 over 2 is really just the midpoint, or the average of the two radii, right? And so you end up with the following: 2 pi times R bar times L. So 2 pi times R bar times L. Or, you know what, let me write it this way. No, I think that's good. So how does this relate to anything that we're talking about? Let's go back to a surface of revolution. So let me remind you guys of what a surface of revolution is, and then we're going to see where this picture of a frustum actually matters, okay? So when you have a surface of revolution, remember you have some function. So let's say y equals f of x is our function, and x is going from a to b, and we take it and we revolve it about the x-axis. So let's look at what we have here. So let's say that it looks like this. This is A, and this is B. And so if you were to take that curve and you were to revolve it around the x-axis, you would end up with something that looks like this. Hold on, I'm trying to draw this well here. So it looks something like, let me try that one more time. Okay, can you guys picture that solid here? And so what we're going to do, let me go ahead and also draw a little red line down there. Let me draw a little red line down there. Okay, so we're going from A to B, and we revolved it around the x-axis, and we're trying to figure out what the surface of revolution is here. So what we're going to do is we're going to do what we usually do, which is partition. So we partition A to B into n subintervals. xi minus 1 to xi. And so just for the sake of ease, I'm going to draw just 4 of these. And what do these look like? So what I'm going to do is I'm going to draw these little dots here. And what we do is we split these up and we look at the shapes that we get, and we're going to connect these with straight lines. And so it looks like this. So we then actually create circles here. The one that I'm going to create, I'll create one right here just so you could see what we're talking about, okay? If we create one right here, for example, if we look at this shape, don't we get exactly a frustum like we had before? Let's look at just this shape. Doesn't this shape right here, if this is x, so if this is x1, this is f of x1, this is f of x2, doesn't that shape exactly give us a frustum? Right? Doesn't that look like one of these? So what's the difference? The only difference is that the function values are the radii, aren't they? So what we're going to do is we're going to take this guy, which I'm just going to call him frustum. Now, notice that this is frustum number 2, but I'm just going to call it frustum number I, okay? So let's draw it. What does Fi look like? We're talking about, let me write it this way. We've got 2 dots here, 2 dots here, and we got so we've got something that looks like this, except this distance, so this radii would be f of xi minus 1, and this radii down here would be f of xi, right? Because it's turned on its side, isn't it? If we go back here, you could see that we actually have f of the different x's, and that's giving us the radii, right? Because that's exactly what this is. It's this distance right here is f of x1, and so on. So this distance right here, the length, we can go ahead and we can call it Li. And if we go back to our picture, This would be L1, this would be L2, this would be L3, and so on, okay? So, yeah, actually, I guess we should start with 0. It's not really going to matter. So, as usual, what we need to do is we need to figure out what these are, these lengths, okay? So let's write down the area of this thing. This guy, based on the formula we wrote down earlier, the area of this frustum is equal to 2 pi times the average of the two divided by, so that's the average of the two, right? And then times the length. But by the last section, section 8.1, we learned that Li is equal to the square root of 1 plus f prime of xi star squared delta x. What is delta x? I guess I forgot to say it, but delta x is what it always is. It's the distance in between. So I'll just write it here with delta x. So these are each delta x. So if we were to look at our picture then, delta x is actually this distance. I guess you could call it the height of the frustum. Okay? Now, what do we think about delta x? Okay? If delta x is small, in other words, the height is really small of this thing, then those two f's are about the same, aren't they? F of xi minus 1 is approximately equal to f of xi star, which is approximately equal to f of xi. So, if we put these two facts together that we just wrote down, then this gives us the following. This implies that the area of the ith frustum is approximately equal to 2 pi times f of xi star times the square root of 1 plus f prime of xi star. And that's going to be squared. And then we have a delta x. So what will the area be of the entire shape? So the area is going to equal, so what we want to do is we want to add them all up. We're going to add up 1 to n of 2 pi f of xi star square root of 1 plus f prime of xi star squared delta x. And then we're going to write the limit as n goes to infinity of that. But this is a calculus class, and we know what this actually means. If you take the limit as n goes to infinity to give you an exact area, this actually becomes an integral. What is it going to be? It's going to be the integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. And so in the end, we get the following. If we go ahead and we call this guy, we just call it y, because we know that y is equal to f of x. And also, remember we had a shorthand notation for this in the last section. We called it ds. We get the nice convenient formula that looks like this, 2 pi y ds. So, this is if we rotate around the x-axis. So what if instead we have a function of y where y goes from C to D and rotate about the y-axis? Then that means that the area is going to equal, it's very similar, it's going to be 2 pi g of y times the square root of 1 plus g prime of y squared dy, or if we want to write it without the y's in there and just with shorthand, right? We know that this is x, and we know that this whole thing is another way of writing, again, ds. We have 2 pi x ds. So let's summarize everything that we wrote down, because this actually leads to different possibilities of how to do each problem depending on what we rotate around and also what our function is in terms of. Okay, but the thing we want to note as we go back is that when we're rotating it around the x-axis, we end up with a y here. So if we rotate around the x-axis, we actually put a y in there. And then if we rotate around the y-axis, then this becomes an x. Okay, so that's a good way to remember the formula. And so I would like to write down a summary. So, summary for the area of a surface of revolution. Okay, everybody. I've taken the time to make a table here, and please copy it down, and I want to explain what is going on in this table. So this is a summary of the different area of surface of revolution formulas. The reason why we have so many choices here is because, number one, we have to look at the problem and see what axis we're rotating about. So if we're rotating it around the x-axis, we're going to use the first row of this table. And if we're rotating it around the y-axis, we're going to use the second row of the table. So if we are rotating it around the x-axis, we know that it's going to be 2 pi y ds, right? And that's what we have here. Now you'll notice that my formula says, or my table says in terms of x or in terms of y in the columns. And that's because even if you're rotating it around the x-axis, it doesn't mean it's going to be in terms of x. So if it is in terms of x, then your y becomes f of x, and your ds becomes the square root of 1 plus f prime of x squared dx. But if it's in terms of y, you use the y version of the ds. However, instead of f of x, you're just going to use the letter y. Okay? So that's what we see in the first row. So you notice that here, if we have in terms of x, we use f of x here, right? F of x. But if it's in terms of y, then we just use the letter y. We don't replace it with the function. We actually just use the letter y. And in the second row of the table, if we're rotating it around the y-axis, then we know we're going to use the integral 2 pi x ds. And if everything is in terms of x, we just leave the x alone. And then we use the x version of the ds. And if everything is in terms of y, then you just replace x with the function g of y. And everything else is in terms of y. So this hopefully clarifies when you would use each version of the formula. Okay, so I'm going to do some examples now where we demonstrate the use of the different versions here. Okay, so example 1. So for these examples, the instructions are all going to be the same. So find the exact area of the surface of revolution. So number 1, we have the curve y equals the square root of 1 plus e to the x, where x goes from 0 to 1, and we are rotated about the x-axis. Okay? All right, so since we're rotating it around the x-axis, I know that the area is going to be 2 pi y ds. Always put the opposite letter there, okay? But everything here is in terms of x, isn't it? Right? Everything here is in terms of x. In terms of x. And so this means that my formula is going to become 2 pi times my function. Let me write it this way. 2 pi f of x times the square root of 1 plus f prime of x squared dx. Okay? So this is going to be my formula. So I need to actually figure that out on the next page. I want to figure out what the square root of 1 plus f prime of x squared is. So let's see what we get. So remember, f of x is the square root of 1 plus e to the x. And so let's go through this and step by step, just like we did in 8.1, so that we are careful about the algebra. So what is f prime of x? So this is going to be 1/2 times 1 plus e to the x to the negative 1/2 times the derivative of the inside is e to the x, which is the same as 1 over, let me write it this way. It's e to the x over 2 square root of 1 plus e to the x. So that's my derivative. Next, we square the derivative, f prime of x squared. If you square that, you get e to the 2x over 4 times 1 plus e to the x, right? Because it's being squared. Which we can write like this, e to the 2x over 4 plus 4e to the x, right? If we distribute that. Next, we have to add 1 to it. So I need to create a fraction with the lowest common denominator. So if you add these two fractions together, you end up with, if I write it in descending order, I get e to the 2x plus 4e to the x plus 4 over 4 plus 4e to the x. But as usual, we know we're going to take the square root of this, and we ask ourselves, does this thing factor? Is this a perfect square? So this whole thing is a perfect square. We notice that this can be factored. How do you factor that? This is just going to equal e to the x plus 2 squared over 4 plus 4 e to the x. And so finally, we take the square root on the last step. So the square root of 1 plus f prime of x squared is. So if you take the square root of that, just to give myself a little more room, I'm going to write it over here. I have e to the x plus 2 divided by, I have the square root of 4 plus 4 e to the x, or 2 square root of 1 plus e to the x. Okay. Isn't that right? Because if I were to factor this bottom, right, don't I have this? 4 times 1 plus e to the x. And so when you take the square root of it, you get that. So everything that you see here is exactly this. So when I go back to the page before, I'm going to fill it in with that. So it's e to the x plus 2 over 2 root 1 plus e to the x. So what is my integral going to be? So I'm integrating with respect to x, so it's 0 to 1, and I get 2 pi times square root of 1 plus e to the x, because that's my f of x right here. And then I have times what I just got on the page next to it, right? Which is e to the x plus 2 divided by 2 square root of 1 plus e to the x dx. Now, you'll notice this looks like it might be a hard integral to solve until we do our cancellation, because the 2 goes away, but also this square root goes away. If we were not careful with this algebra, we would have probably ended up with an integral that was impossible to solve. So if I pull the pi out, I'm integrating something very simple. I'm just integrating e to the x plus 2 dx. So what would that integral be? The antiderivative is e to the x plus 2x, and I'm going from 0 to 1. And this becomes, if I plug in 1, I end up with e plus 2. And then if I plug in 0, I just get 1. So e plus 2 minus 1 is e plus 1. So I get pi times e plus 1. So if we go back to our table here, you obviously don't have to copy this on your own notes, but if I go back to my table here, I rotated around the x-axis, and this everything was in terms of x. So that means that number 1 followed this in my table, right? It was this type. It was x-axis rotation, and it was in terms of x. Okay? Okay, let's do another example. So this one is going to be the function y equals 1 minus x squared. And x goes from 0 to 1. And we are rotating it about the y-axis. So rotated about the y-axis. Okay, so which formula are we going to use? Well, we're rotating it around the y-axis, so we know that this is going to be the integral of 2 pi x ds. Okay. However, you notice that from this, everything is still in terms of x, isn't it? What that means is we're going to leave this as just an x in our integral, except we are going to do 1 plus f prime of x squared dx. Okay, so we don't put the function in there except for the derivative part. This part on the outside of the radical is just an x. So let's go ahead and work out all the algebra on the next page like before, okay? So we're starting with our function f of x equals 1 minus x squared. So let's take the derivative. If we take the derivative of that function, we end up with negative 2x. And then we're going to take the derivative squared. This is 4x squared. And then we're going to add 1 to that. That's just 1 plus 4x squared. And then we're going to take the square root of that. You'll notice that it is not a perfect square, so we just end up with the square root of 1 plus 4x squared. So if we go back to our problem, that's what we're going to stick in there. So square root of 1 plus 4x squared. So this becomes the integral from 0 to 1, because again, it's in terms of x, 2 pi x times the square root of 1 plus 4x squared dx. This is not a hard integral to solve. We recognize that a u substitution is going to work, right? So we're going to let u equal 1 plus 4x squared. We know that's going to work because the derivative is 8x dx, and I see an x dx on the outside. Or 1/8 du is equal to x dx. So then what is my new integral going to become? Instead of 0 to 1, if I plug in 0 into my u equation, I get 1 down here. And if I plug in 1 into my u equation, I end up with 5 up here. What do I get? I get 2 pi, but over 8. And then I have u to the 1/2 du. So what does this give us? I know that that's pi over 4, right? I have a pi over 4 here. And then I know that if I do the power rule on that, I'm going to get 2/3 u to the 3/2. So there's my 2/3 u to the 3/2, and I'm going from 1 to 5. So what is this going to give me? 2 over 4 is the same as 1 over 2, so that's pi over 6 times, if I plug in 5, I get 5 to the 3/2. And if I plug in 1, I get 1 to the 3/2. Or another way to write this is pi over 6 times 5 root 5 minus 1. Right? Because 1 to the power of anything is 1. Or another way to look at it is 1 root 1 is just 1. Okay. That one was pretty simple if we do the algebra correctly, right? None of these integrals have been that hard compared to what we did in chapter 7, but the algebra is the tough part. And also making sure that we use the correct form of the formula, right? Okay, let's do another one. This will be number 3. Actually, before we do the third one, I want to go back and specify which formula we used for that last problem. So if you recall, we had everything in terms of x, but we rotated it around the y-axis. So we rotated around the y-axis, but everything was in terms of x, so this is the one that we did, right? Okay, so let's do the third one. We want the function x equals 1 plus 2y squared. y goes from 1 to 2, and we are rotating about the x-axis. Okay. All right. So because we're rotating it around the x-axis, we know that the area is going to equal the integral of 2 pi y ds this time. But everything that we see here is in terms of y. So that means that my integral is going to be in terms of y also. So I'm going to leave the y alone because it's already a y, and then this is going to become the square root of 1 plus g prime of y squared dy. So I'm going to do g prime, I'm going to do all that algebra on the next page as I usually do. Okay, so g of y is 1 plus 2y squared. G of y is equal to 1 plus 2y squared. So its derivative is 4y. Its derivative squared is 16y squared. 1 plus its derivative squared is 1 plus 16y squared. And then finally, the square root of 1 plus g prime of y squared is just the square root of this, right? It is not a perfect square, so we have to leave it under the radical. So let's go back to the previous page. So this is going to equal, the integral is going from 1 to 2, and I have 2 pi y, and then the square root of 1 plus 16y squared dy. This integral is extremely similar to the one we did in the last example, right? So u is equal to 1 plus 16y squared, or du is equal to 32y dy, or 1 over 32 du is equal to y dy. So what does this integral become? If I plug 1 into my u equation, I get 17. And if I plug 2 into my u equation, I get 2 squared is 4. 4 times 16 is 64, plus 1, so I get 65. And then I get 2 pi over 32, and then times u to the 1/2 du. Very similar to the last problem. I can reduce this fraction. And then when I do the antiderivative, I get 2/3 u to the 3/2. So this is going to become pi over 16 times 2/3 u to the 3/2. And I'm going from 17 to 65 here. So let's go ahead and reduce these fractions. I know that I have a 1 over an 8. So this is going to become pi over 24 times 65 root 65 minus 17 root 17. This is how I'm going to leave my answer. Okay. And just to show you guys which one we did here, because we rotated it around the x-axis and everything was in terms of y, we did this one, right? We did this type. Okay. I want us to do one more example. So number 4, I want to do the function x equals cosine of 1/2 y, and y goes from 0 to pi, and we are rotate about the y-axis. Okay, so we're going to do this first, y-axis. So I know that it's going to equal, remember, we put the opposite variable in here, 2 pi x ds. Okay. Okay, so what now? Everything is in terms of y, isn't it? Right? We've got a function of y, and we also have the y limit. So this is in terms of y. And so what is this going to become? 2 pi cosine of 1/2 y. I'm going to put, actually, you know what? I'll do this on the next part. For now, I just want to put in, I'm going to write that this is going to be g of y, and then 1 plus g prime of y squared dy. So let's do this part on the next page, the derivative stuff, okay? So g of y is cosine of 1/2 y. So g prime of y is what? We need to do negative sine of 1/2 y, but then times the derivative of the inside is 1/2. So this is equal to negative 1/2 sine of 1/2 y. Next, we're going to take the derivative and square it. This gives us 1/4 sine squared of 1/2 y. Next, we're going to add 1 to this. So we have 1 plus 1/4. So actually what I want to do is when we add 1 to it, let's go ahead and combine common denominators here, because I actually have 4/4 plus sine squared of 1/2 y over 4. So that's just going to equal 4 plus sine squared of 1/2 y all over 4. So, is this thing a perfect square? It doesn't look like one to me. So what would the square root of that be? Square root of 1 plus g prime of y squared. I cannot take the square root of the top, so I'm going to write it as square root of 4 plus sine squared of 1/2 y. But I can take the square root of the bottom, it's just 2. So going back to my integral, I have the following. So I have the integral from 0 to pi of 2 pi times the function cosine of 1/2 y. And then I have the square root on the next page. So square root of 4 plus sine squared 1/2 y. And then divided by 2, right? And then dy. So this integral is definitely more complicated, and I want to show you guys how I would approach an integral like this, okay? We're actually going to do several transformations here. The first thing we do is we realize that the derivative of sine is cosine, so I can make this integral easier by doing a u substitution. So what I'm going to do is I'm going to let u equal sine of 1/2 y. And then if I take its derivative, du is 1/2 cosine of 1/2 y dy. Or, well, I could actually leave it like that, right? And so let's go ahead and rewrite the integral using my new notation there. So this 1/2 cosine 1/2 y dy is actually going to absorb everything here that I underline. It's going to take that guy away, it's going to take this guy away, and that guy away, right? So if I do that, I get the following. I get 2 pi square root of 4 plus u squared du. And what about my limits of integration? Well, I can plug 0 and pi into my u equation. So if I plug in 0, sine of 0 is 0. So this stays as a 0. And if I plug in pi, I get sine of pi over 2 is 1. So this is my new integral that I'm doing. It's looking a little better, but it's still tricky, and so I need to use a trig substitution. So for this one, I'm going to let u equal 2 tan theta, and du is equal to 2 secant squared theta d theta. So what is my integral going to become on the next line? So I get 2 pi times, this is going to become 4 plus 4 tan squared theta, and then du is 2 secant squared theta d theta. What are my limits of integration? And this is not super simple because I'm plugging these in for u and then solving for tan, right? So remember, u over 2 is really tan theta. So if I plug in 0, tan of what gives you 0? I get 0. And if I plug in 1, then really this becomes tan theta equals a half. And tangent of what angle gives you a half? It is actually not a simple angle. It's not one of the special angles that we know. So I'm just going to write down arctan of a half. Okay? We're going to need that triangle later on when we actually plug stuff in. Okay? All right, so what does this radical simplify to? This radical right here, after I pull the 4 out, I have 1 plus tan squared, which is just secant squared. And that's under the radical, so that becomes a secant. So that whole thing becomes 2 secant theta. I actually don't need the absolute value because I'm staying entirely in the first quadrant right here, okay? So what am I going to end up integrating? Let's go to the next blank page here. I actually get the integral from 0 to arc tan of a half of 8 pi times secant cubed theta d theta. Now, you may cringe when you look at this because secant cubed theta is not an easy integral to do, unfortunately. This was something, though, that I did in an earlier video. I did secant cubed theta in an earlier video using integration by parts. So you can go ahead and watch the 7.2 video if you don't recall how I did this. But let me go ahead and write down the answer. It was 1/2 times secant theta tan theta plus ln of secant theta plus tan theta. Okay? So rather than doing it from scratch, I wrote the answer there. And so what we're going to get as our answer is, because we have a 1/2 there, if I divide 8 pi by 2, I get 4 pi times, I'm going to get secant, I'm just going to write that all down, secant theta tan theta plus the natural log of the absolute value of secant theta plus tan theta, and I'm going from 0 to arc tan of a half. What does this equal? So arc tan of a half, I'm ready to put this as my angle here, okay? So if arc tan of a half means that tangent of theta is a half, and so I can fill in this missing side of the triangle. This is actually root 5 if I use the Pythagorean theorem. And now I can write down what these trig functions are. So, what is secant of that angle theta? It's root 5 over 2. And tangent of that angle theta is a half plus ln of the absolute value. Secant is root 5 over 2 plus tangent is 1/2. So all of that minus, if I plug in 0, I actually get 0 in that entire thing because I get 0 plus ln of 1. And so maybe I'll just put this just to show that it does become 0. So what does my answer end up being here? If I distribute, this is 4 pi. Let me actually simplify the inside. I get root pi over 4 plus ln of, I can combine those two fractions, root 5 plus 1 over 2. Or if I distribute the 4 pi, I get pi root 5 plus 4 pi ln of root 5 plus 1 all over 2. And this is my answer. That was a very complicated integral, but it allowed us to practice a whole bunch of previous methods from chapter 7. This was the only challenging integral that I did in all these examples. But just to go back to our setup here, remember we had everything in terms of y and we were rotating it around the y-axis. So that means that we actually had this kind of a problem, right? So there are only 4 types, and I did all 4 types, but you'll notice I never even looked at this table as I was doing it because the key here is remembering these circled things on the left, that when it's the x-axis, it's 2 pi y ds, and when you rotate about the y-axis, it's 2 pi x ds, and then you just replace the letters if you need to, if it's in terms of the other variables. Okay, guys, that is it for this video. Thank you so much for watching. I hope it was helpful.